Alright, let's talk about work a little bit. J Random Troll is helping Susie Cream Cheese move, and while doing so, he pushes a box with a force of 250 newtons, and the box slides for 10 meters. So how much work does J Random do on the box? Well, there are a couple of different ways to find work. I could either calculate the change in energy of the box, or I could calculate the amount of force the box experiences times the distance over which it feels that force, times the cosine of the angle theta, the difference between the direction the force is applied and the direction the box actually moves. Well, I don't know a whole lot about the energy of the box because, frankly, I don't know much about the box at all, except that it is box. Instead, I know a lot about the force the box feels and how far it slides, so I'm going to use this second equation to figure out the amount of work that was done on it. Since the box is pushed to the right and it moves to the right, that means theta is 0 degrees. And the cosine of 0 is simply 1. So given that, the work is simply the force times the distance. And with a force of 250 newtons times 10 meters, the work done was just 2,500 joules. Swanky. Well, while J Random is helping her move, Susie utters a snide comment that I cannot repeat as a public high school teacher. J Random decides this is it, he's done with this, and he shoves the box. The box slides 3 meters across the floor, and that's when it stops. Initially, the box was moving at 5 meters per second, so a couple of things about this. How much work does friction do on the box? And what is the coefficient of kinetic friction between the box and the floor? Well, the final kinetic energy is 0, because at the end, the box isn't moving. So the velocity is just 0 there. Minus 1/2 times the mass times the initial velocity squared. Since I know the initial velocity was 5 meters per second, and the mass is 10 kilograms, I can just punch this out really quickly. Let's see, 5 squared is 25, times 10 is 250. Divide that by 2, you get negative 125 joules. And this actually makes sense to me because the box lost kinetic energy. It had it at first, then friction took it away, converted it to heat, and sent it out somewhere else. So it ended up with 0 joules of kinetic energy. Whenever something loses energy, negative work has been done on it. In this case, negative 125 joules of work. Well, the second part of the question is asking what is the coefficient of kinetic friction? Well, now that I know the work that was done, negative 125 joules, I can calculate the force pretty easily. I know the distance that it slid, and here's the trick to this problem, theta. The box, let's say, was sliding to the right. Friction was acting to the left. There's a 180-degree difference between right and left. The cosine of 180 degrees is negative 1. So negative 125 joules will equal negative 1 times the force times the distance. I can just cancel the negatives and set my force times distance equal to 125. The problem says the box slid for 3 meters, so the force is just going to be 125 joules, which is 125 newton meters, divided by 3 meters. When you divide newton meters by meters, you just get newtons, and I'm looking for a force, so that's a good thing. It comes to around 41.7 newtons or so. Well, now that I know the force of friction, I can find the coefficient. The force of kinetic friction equals the coefficient times the normal force. So that means my coefficient is just the ratio of the force of kinetic friction over the normal force. I already calculated this one out to be 41.7 newtons. And the normal force, since this is on a flat surface, and the only two y forces acting on it are gravity and normal, and it's not accelerating up or down, it's safe to say that the normal force is equal to the mass times 9.81. It's equal to the force of gravity. Well, the mass was 10 kilograms, So 10 times 9.81 is 98.1. So all I got to do is divide 41.7 by 98.1, and I got my coefficient. Comes to around 0.42 or so. Ultimately, Susie Cream Cheese does apologize, and J Random accepts. So, in celebration, they go out and play in the snow. Susie sits on a sled, J Random drags it. He pulls the rope with a force of 300 newtons at an angle of 30 degrees, and the sled slides for 5 meters. Since I've got a force and a distance, I'm going to go with that definition of work. But this time, the sled is sliding horizontally. That's the distance vector. But the force is upward at an angle of 30 degrees. So that's going to be my theta value, 30. So the work that was done is ultimately going to be force, let's see, that was 300 newtons, times the distance, that was 5 meters, times the cosine of 30 degrees. Well, when you punch that all out, it comes to around 1299 joules. So that's the way that work might manifest itself. One thing to note is that it's not always kinetic energy that's changing. Work can also be done if something is lifted off the ground. You'd find that by the change in potential energy.